Hello.
Hello, Karthik, we can hear you.
Yeah. So what I'll do is I'll just quickly go through this document, and by tomorrow afternoon, I'll share it with you all. There is again a lot of text here, so I'll just look at. You just need to focus on the for formulas, right? So the equations, and I'll just highlight a few things. Okay, so nothing more than that. So you just need to look at that. Anyway, the document will be shared later on. Okay, so the main thing in in N-term is this statistical learning theory. Okay, so last 4 weeks or so, maybe 7 to 10. Then in weeks 11 and 12, I'll maybe say that first. So what you need to know in weeks 11 and 12 is mainly that randomized response mechanism. Okay, so the randomized response mechanism is what you need to focus on, and now so all the formulas that are mentioned in randomized response mechanism, they should all be committed to memory. Okay, so we won't be giving you any of these formulas during the exam, not even as a part of the question. Okay, so you must know how to compute the probability and what are the various things in that mechanism. So uh, that is, I just wanted to mention that upfront. Uh, that one and this Laplace mechanism also you have to go through, right? But the others you can kind of ignore for N-term, since we also released those videos a bit late, right? So the main thing will be these first two videos. So whatever video you see as data privacy, right? So that is the first video, 1 hour, and then there's a second video, I think differential privacy or something. That's the title here, if I remember. It's 54 minutes. Okay, so those two are the main videos. Okay, so that once that is out of the way, we can focus on this statistical learning theory. Okay, so yeah, the main thing here is that we'll be using probability as an algorithmic tool, and there is some distribution D governing the data set, right? So some joint distribution D. Typically, the way we present or give this joint distribution is by decomposing it into the marginal for the label, and then the conditional distribution for the feature given the label. Okay, so here, for example, this could be Gaussian. The class conditional densities could be Gaussian. Okay, so the contours will look something like this. So this is a bivariate Gaussian, if you recall, and this is some p. So this p could be 0.5, it could be 0.75. So 0.5, it is balanced in some sense. So the way you have to remember this is you have this generative story, right? So you press a button and that determines whether class 0 or class 1 is going to be chosen, and then if depending on the choice conditional on y, you will be sampling a feature, right? So it might be from class 1 or class 0. So that is governed by some PDF. Okay, so this need not be Gaussian, this could be any other distribution. The idea is that there is some T governing features and labels. Okay, so that is the very basic assumption. So what is important is that this is fixed but unknown. So what the prof says in the lecture, I'm just repeating those things. Okay, so it is fixed, meaning there is something called D which is out there. That is what we are assuming, but it is not known to us. So if it is known to us, then we could as well make use of that and find out what are optimal classifiers, right? So it is unknown, but there is something called D. Okay, so the setting in the rest of these weeks is always something like this, right? So there is some feature vector in RT and the labels are in 0, 1, and you draw IID samples x1, y1 to xn, yn. Okay, and H is usually we have seen F refer to some classifier. In this case, all our classifiers will be referred to as H. Okay, going from the feature space to the label space. So that's the basic setting for all of these problems. The rest of the discussion in statistical learning theory. So the first kind of formula or equation that you should know is the error. Okay, the error is nothing but the likelihood of your classifier making a mistake. So this is the probability of your classifier H making a mistake on data point x comma y. right? So this is the test error. Okay, so on an average, so one way to understand this is if you keep drawing samples IID from D, and if you find out the number of errors, the average number of errors made by H, that will be an estimate for the test error. Okay, so that's by law of large numbers. The more number of data points you take, the closer or better will be your estimate for the test error. Right? So this subscript D denotes test error always. And what goes inside is some classifier H. Okay, so that is the test error. Now, given a set of data points sampled from D, that is S, you can define the train error. Train error is again the same thing, average. So it's the average misclassification rate. So that, or rather the misclassification rate or the average number of data points that are misclassified by H. Okay, the subscript S always is going to denote the train error. And this is also something you have to be comfortable with, the indicator function. Right? So it is 1 when there is a misclassification. So that's regarding the train and test error. So yeah, once you have the train and once you know what you define what the error is, you can then ask what the optimal classifier is. So the optimal classifier is something that can never be computed in practice. Okay, in practice you don't have access to the data set, the distribution D that generates the data. Okay, so this is all theory. In theory, so the optimal classifier is the one which minimizes the test error, and that's called the base classifier H star of X, right? So it is one when the probability of y equal to 1 given X is greater than or equal to 0.5. Actually, this is the same as saying that P of y equal to 1 given X greater than or equal to P of y equal to 0 given X. But then since there are only two labels, that will boil down to greater than or equal to 0.5. Okay, so this is intuitively, this makes sense, right? So if your underlying distribution is telling you that label 1 is more likely, then it makes sense for you to predict 1 and 0 otherwise. Okay, so the error incurred by the base classifier is the base error, so that is denoted by error D star. That is the test error of the base classifier. Okay, and once again, we don't have access to this. In theory, this is all we can do in theory. Okay, in practice, we cannot do this. Yeah, yes, sir. Yeah.
Sorry, because this is a question from the lecture too.
Yeah.
Sometimes we use plus minus 1, sometimes we use 0, 1. I understand binary classification doesn't matter. And it seems to none of the formula or anything will change if we use 0 rather than minus 1. I just want to confirm that, because here also I think professor uses plus 1 and minus 1, but you use 0 and 1.
Yeah. So
I think it will be the same, right? I don't think there's any difference between those two. I just want to confirm that.
Yeah, no difference. But for the exam, I think, to my knowledge, we have only used 0, 1 throughout the exam. But yeah, it shouldn't matter. Okay, so that is regarding the base error base classifier. Okay, so even after having said all this, we still are going to try and find out what the base error and base classifier are. Okay, so I'll just take one sample problem. This is like a prototypical problem. Okay, so how do you find these two objects when you are given a question? Okay, so typically what we do is, it's convenient to decompose the joint density or the joint distribution this way, right? As I mentioned before. So the generative story is that you flip a coin with probability P of y and you determine which class to select, and then with that probability you select that class, and then having selected that class, you generate a feature or a data point from that class with this probability, right? So depending on what exists, may either be a PDF or a PMF. Okay, so but this is how we decompose it. Okay, this is one way. We could also do it as P of X and then P of Y given X, but then that's a bit tricky, right? This is more intuitive. So that is, once that is there, you can now ask what is the base classifier. So this we just discussed, right? So the base classifier is one which gives you for that you need to find out when this is greater than this, right? So earlier, this is actually the same as saying P of y equal to 1 given x greater than or equal to P of y equal to 0 given x, because these two sum to 1, right? So these two sum to 1. So if this is greater than or equal to this is same as saying that this is greater than or equal to 0.5. Okay. So what you do now is you just use Bayes theorem, and you can swap x and y. Okay, so it now becomes P of x given y, P of x given y. So this is what you end up with. Okay, so why is this easier? It's easier to, instead of dealing with P of y given x, it's easier to deal with P of x given y because of the way the joint density has been decomposed. Okay, it has been decomposed as class conditional densities, right? Like this. Therefore, it is easier to work with P of x given y rather than P of y given x. Okay, so when you have a problem of this form, what you have to do is you have to arrive at this somehow, and then it's kind of easy. So you just need to find out under what conditions P of x given y will be greater than or equal to this. Okay, so if you take a particular example, this was there in the assignments, right? So for example, x given y equal to 1 and 0 could be two normal distributions, in which case it'll boil down to this, right? So if your P of y equal to 0 is 0.5, then this whole thing will vanish. It will become 1. So you'll be left with this one. Okay, so you'll be left with this, and all this is saying is when is my green curve? This is my PDF, right? When is it above my red curve? That is what this is saying, right? So whenever that happens, I'll predict 1. So for this entire region, I'll be predicting 1. Region meaning x-axis, right? So there's only one feature. So this whole region will be 1, and then this whole region will be 0. Right? That's what this equation means. And your classifier in this case is a decision sum. You're just x less than or equal to theta, or x greater than or equal to theta, something like that. Okay, with theta being wherever these two intersect. Okay, this is only a special case. Please don't get carried away by this. I'm just showing you this for a very specific case of this being equal and the class conditional densities being Gaussian, right? So it's what you have to, this is generic, right? This holds for any case, but what you see here holds good for only this particular example. I hope that is clear, right? So then you come to the Bayes error. Okay, once you have found out the Bayes classifier, you can now use that to find the Bayes error. So the Bayes error, right, though it is defined this way as the probability of a misclassification happening, it is easier to think of it as an expectation. Okay, so remember that the expectation of an indicator random variable is the probability of that event happening. So this is an event. Okay, this might be confusing. This is, so this h star of x not equal to y, you can think of it as an event. Okay, so the set of all misclassifications in some sense, right? Where all across all possible, so you're kind of combing through the entire probability space, right? And you're looking at all those cases where h star of x is not going to be equal to y, right? And then you're asking what is the probability of that event. So alternatively, what you can do is you can treat that as an expectation. So this is the indicator random variable of a mistake happening. What is the expected value of that indicator random variable, right? So these two are same. This is basic probability rules. You can, I hope this is clear to you, right? So how we go from here to here. Okay, so once you do this, things become easier. You can now expand this expectation across xn. So this is a joint. So remember, this is a joint distribution, right? So you're now expanding this expectation. So there are two variables. So that you have y and you have x, right? So how does it work? Once again, this decomposition will help you. So always use this one. So first you do P of y. So you express P of x comma y as P of y into P of x given y. So that is what we have done here. Instead of P of x given y, I'm using f because it's some density, right? So it could be Gaussian. If it is Gaussian, it is 1 by root 2 pi sigma square e power minus x minus mu whole square by 2 sigma square. That will be f, right? So depending on what class conditional density is given, you should substitute that with f, the density, corresponding density, or PMF if the distribution happens to be random variable happens to be discrete. Okay, this is fine, right? What I have done here, I have just expanded p of x comma y. Okay, so notice that there is a summation here, but an integral here. So that's because y is discrete, right? Y can be only 0 or 1. So that's a discrete random variable. X, I'm assuming it to be continuous here. Okay, so that's why the integral. And then what happens is you can nicely separate this into two values. So one is for p of y equal to 0, p of y equal to 1. That summation is expanded, that's all. Okay, so that is all there is to ER D star. Okay, is this clear to everyone? If it's clear, you can just let me know. Thumbs up. I'll just move on. Not clear to anyone? Okay, right. So you just need to stare at it for a while. This is there in the assignments also, right? We just solved one in week 10. There was a question based on this. So if you look at this example, it might become clear. So what is it saying? There are two terms, right? So if you look at this term, p of y equal to 0, and that integral, what is this integral? So p of y equal to 0, assume it's 0.5, right? So this is 0.5, 0.5. So you're not worrying about that. So what is this integral going to mean? It's going to mean the following. You're looking at all those places where, so see, this integral is over the entire support, okay? Meaning it will go from minus infinity to infinity. And you're only interested in those regions where h star of x is not equal to 0, right? Only then this indicator will be 1, right? So where is h star of x not equal to 0? So here it is 1, okay? And here it is 0. So here it is 0, so I am not interested in this. So I am only interested in this region. For the first integral, I am interested in this region, okay? And what am I integrating? I'm integrating the density of x given y equal to 0 in this region, right? So once I identify the region, this indicator becomes 1, okay? So I no longer need to worry about the indicator random variable. So once you have identified the region where there is a misclassification, not a misclassification, more of once you have identified the region where it is not equal to 0, right? So this is the region where h star of x is not equal to 0. So once you have identified that region, all that you need to do is calculate the area under the curve for this PDF. Okay, that is nothing but this area. Okay, so that is how the first area comes about. Second area is nothing but h star of x not equal to 1. So in this region, h star of x will not be 1. Okay, and you're integrating the f1. So this density, this green density over this region, right? That's how this area comes about. Okay, so if you know sum both of them and multiply them by 0.5, that will be your base error. Okay, so I hope this equation is now slightly better, is clearer with this example. Okay, so this is how you find, if you are given a distribution, this is how you have to find the base error and the base classifier. So two remarks that you have to keep in mind. One is, if x is discrete, then the PDF will be replaced by the PMF. So this, not just this one, this integral will become a sum. Okay, if x happens to be discrete. That is one remark. Second one, again, whatever I've been mentioning, right? So D is fixed but unknown, and you can only do this in theory. You can't do this in practice. Okay, so that is with respect to one very important concept called the base classifier and base error. Okay, so then we have error decomposition. So you have, start looking at some classifier HS that has been trained on a data set S. Okay, so RS HS will be your train error that we already know, and we introduced two other quantities, right? One is RD star, which we already know is the base error. Now we introduce RDH, right? So you have some hypothesis class. Hypothesis class is just a collection of classifiers, some collection of classifiers, say linear classifiers or different kinds of classifiers, right? It could be anything. So in our case, set of all decision entries, that could be another H. So RD of H is the best classifier from H, right? That which achieves the minimum test error. Okay, so that's what RD of H means, right? Whenever you see D here, it is test error. Okay. So what is the error? What is the difference we are interested in? We would like to get close to the base error, but then what we have handle over is the train error. Okay, that's the only thing we can compute in practice. But then what we want to achieve is the base error. Okay, so therefore that's why we consider this difference, and that difference can be broken down into three differences in turn. So what are they? They are called the generalization error. So generalization error always takes the form RS minus RD, okay, of the same classifier. So it tells you how different the performance of a classifier is on the train and test cases, right? So this is like, remember, okay, I'll come to that later. Yeah. So that is the generalization error. What is estimation error telling you? It's telling you how far the test error of the classifier is from the test error of the best possible classifier in your hypothesis. That's what it is telling you. Approximation is telling you, error is telling you what? So you have the best possible classifier in the hypothesis class. How far is it away from the optimal classifier overall? That's the base classifier, right? So that one. Okay, so each one measures a different quantity, and so just to give you a sense, if you have a very complex classifier, right, say a neural network, neural networks are going to have very low approximation error, right? So they can, if they can kind of fit any distribution, so they'll have a very good approximation error. Now, if you take a linear classifier, let's say, right, for a very complex problem, then the approximation error might not be that good. However, a linear classifier might, you might be able to have very good generalization error, but then the approximation error is going to be quite high, the absolute value, right? So there is some trade-off, or there is some interplay between these three errors. So the rest of the weeks, what the prof has done is he has taken each error in turn and tried to analyze that. Okay. So the maximum time he has spent on generalization error. So what is this generalization error? It is this RS HS minus RDHS, right? So the problem with this quantity is that S is random, so HS is also random. Therefore, this RS HS is also going to be random, okay? And so is RD of HS, right? Because HS is again, so even though this is a single value, it's still going to have some randomness because of HS, right? So what we do is we get rid of HS and just study the generalization error for some arbitrary classifier in the hypothesis class. So that is this. Okay, so what you need to remember here is there is a lot of proving stuff happening, right, in the lecture. So what you need to know finally is that in expectation, remember that RS of H is now random, but the expectation is over what? It's over the data set S you are sampling. Okay, so that's where the randomness here is. Okay, so the randomness is coming from the way you sample each data point from D. So if you now look at this expectation on an average, so what is this telling you? It's telling you that the expected value of the train error is actually the test error. So in some sense, it's unbiased, right? So estimate of the test error. So this fellow is a unbiased estimator of the test error, okay? Which is a good thing. Why is it a good thing? Because if you take a classifier H, and if you compute the train error, on average, right? If you repeat this experiment like thousands of times, on an average, the train error is a good proxy for the test error. That's what it's telling you. Okay, that's what the average is. But then it is not enough if the average is the same as the test error. There could be high variance, right? So the mean could be the same as the test error, but that doesn't guarantee that variance is small. So if you want to know how much it varies from the mean, you need concentration inequalities, right? So this is the mean. Remember that this is a scalar value, it's not random. And this is a random variable. Okay, so you are asking how far is my train error away from my test error? On an average, I know it is the same, but then what is the deviation? So that is what this is measuring. Okay, the generalization error is measuring the deviation of your train error from test error, right? So the great result is that this is actually bounded. Okay, so and it grows in it kind of is inversely related to the number of data points. So with some more math, what you can show and what you need to remember for the exam is this part, right? That with the probability of the generalization error being more than something, right, is going as this, right, for a finite hypothesis class. So finite hypothesis class meaning there are only finite number of classifiers in H. Okay, so what you need to know is the exponents and all that. So the whole expression you need to know. That is one thing, and this you can derive, right? I don't think you need to remember this. All that you need to do is set this less than or equal to delta, take log on both sides, you will get this expression, right? You don't need to mug up this part, but this one you need to remember. If you remember Hofding's inequality, you are going to remember this e power minus 2 and epsilon square either way. So yeah, so what you need to know or what you need to know beyond this is that what is this telling you? So what is this telling you? It's telling you that where I have written this somewhere. So yeah, this is what it is telling you. The train error for a finite hypothesis class, this theorem tells you that the train error is a good proxy for the test error. Okay, proxy meaning you can't compute the test error, but then what you can do is you can compute a train error, and then it will be kind of close to the test error with high probability. That's what it's telling you. This is a good thing. Okay, because so that's one thing it's telling you. The second thing it's telling you is when can you achieve this? You can achieve this when you have a large number of data points. Okay, so that this bound is also interesting because the interplay is quite clear. The smaller you want the error to be, the more the number of data points you need. Okay, likewise, the smaller you want the probability of this happening to be, the greater the number of data points you need. So that's why both epsilon and delta come in the denominator. Okay, and the bigger the classifier class, the hypothesis class is, the more difficult it's going to be, right? Once again, a more complex hypothesis class, what will happen? It's going to be harder, so it will fit your data set, training data set very well, right? So there's going to be a lot of variance. If you recall your bias variance trade-off that you studied earlier, the more complex your classifier gets, the better it is at fitting noise in the training data. Therefore, there's going to be more variance. So there'll be the training error might be very low, but then the deviation from train error and test error might be high. That's why this H appears in the numerator. So the more complex the class, the more the number of data points that you need so that you can achieve this generalization bound. Okay, so that is the second point you need to note. The final point is this point, right? This theorem tells you nothing about the goodness of a classifier. Okay, so it doesn't tell you if the test error is small or large. There is no claim made by the theorem about the test error. All that it tells you is the train error is going to be close enough to the test error. That's all it tells you. So it's Okay, so which is why you need to know that this line you need to remember. The train error is a good proxy for the test error. That's all it says. Okay, so that's for a finite edge. And the rest of the lecture is devoted to understanding how we can extend this to infinite hypothesis classes. So that's where this whole idea of VC dimension comes in. So what is the VC dimension? Yeah, so first we look at one example of infinite hypothesis class. So this is the H interval, the interval hypothesis class. What is that? It is just, it's going to predict one if the data point falls inside an interval A comma B, zero otherwise, right? So what is the VC dimension idea? So the prof introduces it in the form of a two-player game. So maybe I'll just first present that. So what are we trying to do? You have two players, right? So player one is always going to choose points, and player two is always going to choose a set of labels for the points. Okay, so the goal of player one is to choose the points in such a way that no matter what labels player two comes up with, he can always classify the points perfectly. Okay, so remember that player one has the liberty to choose the points in whichever way he wants. Okay, so he's not going to be blocked by that fact, right? So player one has complete liberty to choose the points in whatever way he wants, but he can't label them. He has to choose the points in such a way that every labeling can be perfectly classified by some classifier in the hypothesis class. So that's what player one should target. Player two, on the other hand, has no control over the points that are given to him, but he can do whatever labels he wants, right? So labeling is under his control. So that is the basic motivations of these two players. So they start with one data point. So player one has to choose one data point, and player two has to label that. So they keep going on. So if player one cannot choose a set of data points, then the game stops, right? So if that happens in round k plus 1, so k plus 1th round, player 1 fails, okay, or player 1 loses. He's not able to, no matter what set of points he chooses, no classifier is able to perfectly classify that set of data points, right? So in that case, the previous round, whatever the previous round is, that will be the VC dimension, okay? So this prof has explained it very well in the lecture. So beyond this, I don't think I need to go and look at it. So these are the formal definitions, right? So sometimes some of you might be more comfortable with the formal mathematical definitions of the VC dimension. I'll leave it to you. You can read it up later. Okay. So what are the important classes that you must be aware of? One is H interval. So that has VC dimension 2. So if you give two data points, player one can still find a classifier, okay, that will perfectly classify. So no matter what it is, so the points could be plus minus, it could be plus plus, it could be minus minus. No matter how you label those 2 points, I can always find a interval surrounding appropriate points, right? So that's why the VC dimension is 2. If you give me 3 points, then something like plus minus plus would fail, right? So with plus minus plus, I can't find a single interval that separates the points properly, right? So perfect. So that is why it's 2. Likewise, this is the axis parallel rectangles, right? So where this is how you formally specify it. So first coordinate is between AB, and the second coordinate should be between C comma D. So that's how you formally specify the axis parallel rectangles. Everything inside is 1, everything outside is 0. So you can kind of argue and show that VC dimension of this is 4. And next thing you need to know is linear classifiers, right? Passing through the origin. So that has VC dimension D. He has proved this in the lectures. Now, if it is not passing through the origin, there'll be a bias term. So that will add one more degree of freedom. So that therefore, in that case, this will become d plus 1. Okay. So that is, these are some important classes. You must know how to compute the VC dimension also, right? So it's not enough to know that it is 2, 4, D. So you have to go back and study how the prof actually arrives at these numbers. Okay. It could be by means of playing that game or otherwise, but you must know how to do these things. Okay, so why is that useful? It's useful because you can extend this uniform convergence result for infinite hypothesis classes with finite VC dimension. So this is the most important part. If your VC dimension is finite, then notice that the left-hand side is the same, but in the right-hand side, instead of mod h, you have n power d, right? So the idea is that even though this goes down as n power d, as n tends to infinity, this is exponential, right? So this will go to 0 faster. So the whole thing will tend to 0. Okay. So your this generalization result still holds. So the train error is still a good proxy for the test error, as long as the hypothesis class that you are using is finite VC dimension. Okay, it has finite VC dimension. Okay, so that is the VC dimension business. With that, the generalization error discussion is over, and then the prof moves to estimation error. So in the estimation error, the main concept is this idea of empirical risk minimizer or ER. Okay, so the estimation error, if you remember, is the test error of HS minus test error of the best classifier in H. So notice that he would have mentioned that you can't get a concentration inequality directly for the simple reason that this is a constant, or this is a fixed point, whereas this HS is random, right? So this will, depending on what data set S you have and what HS you train from that, this will lie at various locations, right? So you can't get a concentration inequality for this directly. So he would have done few things, right? So the first thing that he would have done is to simplify this problem. Instead of looking at HS, the first thing you do is you specify an algorithm, right? So after all, you are estimating a classifier from a hypothesis class. So how do you estimate? What algorithm do you use to estimate? The simplest algorithm that you can think of is minimizing the train error. Okay, so that's the only thing you have. Train error is the only thing you have control over. So you would instead of thinking about other algorithms, the one obvious thing is minimize the train error. Whatever classifier minimizes the train error, you call that HSER. Okay, so you have to be careful here. This is H is drawn from the hypothesis class. Okay, it's not. So the ERM is not the base classifier, right? It could be the base classifier, but then the ERM is not that, right? Always, right? It is some classifier from your hypothesis class which minimizes the trainer. Okay, so be careful about this part, right? This condition where you are drawing the ERM is important. So once that is there, again with some math you can show that the test error of the ERM and the best possible classifier, so they are close to each other. Okay, as n tends to infinity, they are close to each other, right? So that is what you can show. So this is what you wanted to show for any HS, but then instead what you have shown is for the ERM this happens. Okay, so here what should you remember from the exam point of view? This equation is something you have to remember. Okay, of course, the ERM's definition you need to know. What is the ERM and how to compute the ERM given a hypothesis class? And then what's the result for the estimation error of the ERM? That is also something you need to do, right? So on the right-hand side, notice that you have the generalization error. So the uniform convergence theorem again, right? Because this is whenever you see RS minus RD, it is generalization error. Okay, and this is some upper bound is there, right? Because H is, of course, you have to mention this finite VC dimension part, but as long as H has finite VC dimension, this will be less than or equal to some blah blah blah. Okay, so that will hold. Okay, there is some more interpretation I've given here. Maybe you can read it later. That is the interpretation. So the problem with this from a practical standpoint is that ERM is hard to compute, right? It's computationally a hard problem, minimizing the train error, right? So if you remember from MLT, we call this train error the 0-1 loss, right? So minimizing the 0-1 loss is hard computationally. Therefore, we look for surrogate loss functions that are convex, which admit easier optimization strategies, right? So that is it's a different trajectory, but you just need to know that fact concerning the ERM. Okay, so the final point that you need to know is this sample compression business. So I have skipped the generalization error part. That's not like too important. Prof himself didn't spend a lot of time there. So
you mean approximation error part?
Sorry, yeah. What did I say? I said something.
Generalization.
Sorry. Yeah. Sorry, yeah. So generalization error is very important. The final error, yeah, the approximation error, right? So the structural risk minimizer and all that, right? So that is important. Like you can learn that part, but from the exam point of view, we didn't test it in the assignments also. So it's like very tough to ask questions from that. So you can just get an idea of what it is, how regularizers come out of that idea. So you basically have increasing VC dimension classes, right? So classes with increasing VC dimension, and you also include some penalty term, right? So this ERM to SRM, Prof has done something. So you can refer to the lectures. It's good to know, but for exam, we won't test you on that. Okay. So yeah, final part is sample compression. So the key idea here is that, see, the VC dimension captures what? It captures the complexity of a class. So the higher the VC dimension, more complex or greater is the learning capacity of the class. Okay. And we have already shown that, or we have already discussed this fact that if the VC dimension is finite, then the class is learnable. So meaning what? Learnable means the train error is a good proxy for test error business, right? So that's what we. Okay, so what finite VC dimension means the class is learnable, learning can happen. That is one side of the coin. The other side of the coin is this idea of sample compression, right? So if you claim that your class is learnable, so then I must be able to, compress the information in the data set into a few data points, right? Into a subset of data points. So the idea is you're bridging two different concepts. So compression is the ability to compress a data set is indication that you can learn from that data set, right? So something along those lines, right? I don't think I have explained it properly, but right. So the formal mechanism here is following, right? So whenever you discuss sample compression, you have to note that the data set is, you are always having some hypothesis class in the background. Okay. The data set is, yeah.
If I can, if you don't mind, what Professor said, because I just reading it just now, says if we can do a compression with a specific set, right, then we can go and say that it is learnable.
Right.
And that means, and that's what we want to know, right? So if we can compress, we can learn it, and we are happy with that, right? Whether learnability implies compression is something that is, he kind of left it saying that it is theoretical and it has not been proved. He actually said that hypothesis has been there for 30 years or so, and people have not proved it. So,
okay, right, yeah. Okay, so here we will have this H. in the background, and this S will be such that the labels are drawn from. How are we getting these labels? So the labels are given by some H in capital H, right? Or whatever this is. So these are not random labels. Right? That's the first thing you have to know. So we are only studying all labelings that can be generated by classifiers in our hypothesis class. Okay, that's what we are interested in. So in the context of sample compression, whenever we talk about S, we will be using yi to mean this specific yi, right? So h of xi will be equal to yi for all I 1 to n. Okay, so you have to keep that in mind. This is only for sample compression discussion, right? Not otherwise. Otherwise, it's different. But here we are looking at data points that have been labeled using a classifier H from our hypothesis class. Can we compress such a data set? That's the question. Okay, so there are two algorithms. One is compression, another is decompression. Okay, so there is one input which is S, and the output is two things. You have to output a data set T, which is a subset of S, and you have to output a classifier H prime. So the idea of this compression decompression pair is H prime should give the same labeling as H on all data points in S. Okay, that's the deal. But then the only thing that H prime has access to is T. Okay, it doesn't know what S is. It has no idea. The decompression algorithm has no clue what S is. Okay, it has only access to K data points that are in T. Using those K data points, it has to recover the labeling of all data points in S. Okay, this naturally results in some compression, right? You are throwing away some data points. If you can do that, okay, if such an algorithm pair exists, then we say that the hypothesis class is having a sample compression scheme of size K. Okay, so few points here. I will just define this here. See, this is at most K. Okay, you have to remember this. For some data sets, you might be able to do this with a smaller value of K, but then the whole thing is, the whole point is you must be able to do it with at most K data points in T. Okay, that's point number one. Point number two is that this compression decompression pair should work for every S that is passed as input to the algorithm, right? So every S where this, you have to always remember that S is here generated by some H in the hypothesis class, right? It's not some arbitrary data set. That's not what we are asking. What we are asking is, for every data set generated by the hypothesis, some hypothesis in the hypothesis class, some classifier in the hypothesis class, can you give me a T and a H prime? Okay. So these two algorithms therefore should work for any S. Okay. So just two examples that the prof gives. I also mentioned this briefly. One is HINT, right? HINT has a sample compression scheme of size 2. So what you would do is, you given a data set that has been generated by some classifier in HINT, you take the widest 2 points that belong to the positive class, and then you return the classifier H prime as Hx1, x2, where x1, x2 will be, x1 will be this, x2 will be this, right? So maybe I should call this x1 here, x2, right? Now, there's one remark which I don't think we mentioned this earlier. So note that this compression decompression algorithm will fail, what as given here. It will fail if all the data points in S are negative. I belong to red or class 0. Okay, so see that this compression scheme is choose 2 points from the positive class. That's how I have defined it. But what if there are no positive points at all? Then this entire thing will fail, right? Okay, so Therefore, what I'm trying to say is this is not a comprehensive algorithm, meaning it doesn't cover all corner cases. Ideally, that the correct algorithm will have covered all corner cases, right? So, for example, what could be a corner case? So I'll delete this later. So I'll not, this will not be a part of the PDF that I share, but I just want you to keep this in mind, that the fact that it should work for any S, that is, let me think of something like only one, right? Again, this compression algorithm will fail because there are no 2 points. Okay, so this is one corner case. Another corner case could be no data points belonging to the green class.
One it will still work, right? Because you can just put it around it. It will still work.
Correct, but my
all negative will definitely, it will not work.
Yeah, so even one, right? I should. Yeah, you're right. So I can choose. Yeah, I will end
just
up
one
choosing
point that you just put that
correct, yeah.
around, like a small delta around it, that will still work. Yeah.
Right. Yeah. So for one, this will work. For this, it will fail. Right. So you have to. What you will have to specify is you'll have to have a case in this, right? It should be some if-else ladder. So if all the points are, if there are at least, or if there is at least one green point, then do this. That will be the comprehensive algorithm, right? So if at least one green point, okay, then you will do this. If not, then what you do is, you could choose the biggest red point, the point with the maximum x value, and then just add a bracket. So x plus epsilon, x plus 2 epsilon, right? Something like that. So you get that, right? So it will be, so let's say this value is a. Your classifier could be, it could start here, right? It could be some a plus epsilon, comma a plus 2 epsilon. That could be your interval classifier. Right, that will work. That will be a small bracket here, and everything will be 0 outside that. Then it will work. Right. So your decompression algorithm should also change. Should it change? Yeah. No. So in this case, it need not change, but in some cases, it might have to change. Okay. So so please keep that in mind.
Yeah, decompression is actually selecting the hypothesis, right? The hypothesis has to change appropriately.
Yeah,
I mean, decompression, actually, we're not putting a decompression algorithm as such. We're not trying to get back S from the sample, compressed points. We are trying to find the algorithm. So the one that you mentioned, the last example that you gave. So if I am given only one negative, if everything is negative, I am given the last negative class. Then I set the positive to be slightly above that.
Yeah,
I can be given the lowest, the first negative also. Then I go this way.
Correct.
Everything,
Yeah.
both will work.
Yeah. So I would return. I would return t as just x, say x comma 0, right? So some a comma 0, and then depending on that, the decompression h prime I should make. So again, there should be an if else here, is what I'm saying, right? So there should be a. So if the label is 1.
Yeah, that's right. Yeah. So we
right?
have to
So
have
you have to have some kind of an if else. Right. So but then all that the prof said is valid. All that I'm trying to convey here is the compression algorithm specified in the lecture is not necessarily complete. Okay. So you will have to complete it. So this is still true. So this is not false. This is still true. But then you'll have to take care to define the compression and decompression schemes properly. Okay. So that is regarding H-int. HAPR, again, same thing. So if all are negative, you'll have to be careful. But let's say there are at least 4 positive points. Then your compression scheme will look something like this. So choose the widest from, I will add a few more points here. Yeah, so choose the widest from both axes, and then specify that as HAPR. So A, B, C, D, this will be A, B, that will be C, D. So this has a sample compression scheme of size 4.
Is it widest from the both axes? I don't know whether there's a question on it. I thought I can take the center of the rectangle and get the farthest 4 points from there. Farthest 4 positive points from the center. So that will give the same.
Center of, how would you compute the center of the rectangle?
Because I have been given, right? Oh, you have not been given the rectangle. Oh, I'm just given the points. Okay, I get
Yeah.
it. Okay, thanks.
Right? Yeah. So yeah, so if this is the final result, right? So if you know that there is a sample, if you know that the data set can be compressed, then it is learnable, right? Because compression, that is one side of the argument, right? So that is apparently has been proven. It's a proven result. But what we don't know is, if you have a finite VC dimension, then we already know that it's learnable because it has finite VC dimension, but it's also compressible in some sense, right? Do you have a compression scheme of size k if you know that the VC dimension is size k? So that part still remains a hidden mystery. So people are still looking for it. Okay, looking to finances for it. So yeah, so you must know how to find SCS for different classifiers. Okay, so that is something you have to know. You must know how to find out the VC dimension. You must know how to find ERM. You must remember these inequalities, the uniform convergence results. Okay, what else do you need to know? Yeah, you need to know what generalization error is, what these three errors are. You need to know how to compute base error base classifier, and what else? Train and test error. Yeah, so that is what you need to know from the last 6 weeks. And the randomized response mechanism. Okay, so that's all I wanted to say. I wanted to share. So any questions from your side? Yeah.
Yeah, regarding that compression. So in week 10 graded assignment, there is one question like the class is like right angle triangle.
Right.
They ask that what is the compression scheme of size? Like what is the compression size? Like as per you said, like we have to take the farthest points from like related to axis. So if you take that, it will be 3, right? But the answer is 4. Could you explain how it will be 4?
So everything inside the right triangle is 1, right?
It's 10 o'clock.
That question, no? Okay, so that problem. So if you are given 3 points, there is no problem, right? So the question is, let's say you have, okay, so let's see if we can do it with just 3 points. Okay, so let's say you only focus on the green points, right? So how would you construct the right triangle here?
This may not be possible with the points just by taking the points compression with 3 points. Like it won't be a right angle triangle like with the side facing the axis, right?
Yes, sir. In the question, it was given that the hypotenuse has a negative slope. So we can make a right angle triangle that the leftmost point, we can just draw a parallel line which is parallel to y-axis, and below one is a parallel to x-axis which goes from this point, and the slope is negative and which goes from those two green points. So it will make a right angle triangle.
Correct.
In that question, it is given that hypotenuse has a negative slope. So
Correct.
if it has a negative slope, then those 2 points, it will go through those 2 points, and we can make two base and perpendicular based on the x-axis and y-axis parallel to those.
Yeah, see that's correct. So what will your T be here?
T means that scheme, compression scheme.
Yeah,
You
what
said?
will be your, what subset will you output here?
Only these 3 points then. These 3 points.
Okay. Now how
Three
will you?
green points.
Yeah, that is correct. How will you describe the deconstruct the? How will you get the H prime from this?
We can take just the right angle triangle. These 3 points only.
Yeah, tell me the
And
procedure.
so this using this below points, like we can have x-axis parallel to x-axis and y-axis, and the negative slope is negative, so we can have a right angle triangle because we would have a slope for this line, hypotenuse, and
So the point has to, the hypotenuse has to pass through these two.
just yes. We can extend this line and take the intersection with the line which goes from the bottommost point.
Correct. And then the horizontal has to lie here.
Yes, yes.
Okay.
And yeah, one line parallel to y-axis.
And okay. Yeah, let me think. What did I ask in that question?
In that question, it is asked that what will be the compression scheme, and answer is 4. And in the solution is also given. I was not able to understand this because I have also entered 3, but the answer is 4.
Yeah, once again. What did I ask? Is that image? Okay. Okay, so it should work for any data set, right? So I have given you a data set for which it works with 3 points. Now the skill lies in choosing data set for which.
Take a 3 points that is in the same line, then we need a 4th point to identify the triangle.
Yeah, so something like this is what I have in the image. So yeah, what will be the algorithm now?
Here also we can take this the leftmost point and draw a perpendicular line parallel to y-axis, and the bottommost point and line parallel to x-axis, and the hypotenuse will have the
First tell me
leftmost
which 3
nearest
points
one.
are going to be in T.
Which 3 points? Sorry.
Which 3 points are going to be in T?
In this case, I guess, yeah. In this case, I think it will be 4. Then because the hypotenuse will pass from those 2 points, and those 2 points are required to know the slope.
Yeah, so that's why the answer is 4. So S. So the S has to be less than or equal to. So S can be anything, but you call it SCS of size K, provided in the worst possible case, even in the worst possible case, you have to give only at most K points, right? So this is kind of the worst possible case.
Yeah, okay, got it. Thank you.
But here also we can draw it with 3 points, no?
Which 3?
So we have to iterate, which gives the maximum coverage. given the 4 points, we can iterate on the two which one of them we want to pick, right? We have that choice.
You have the choice to output any t you want.
Right. So I have the 4 points as input.
Okay, yeah, you can tell me after you perform the iterations which 3 you are going to give.
I will give the one which gives the maximum height and the width.
Yeah, you can tell me here, right? Which one, which of these 3?
So first I will draw a line parallel to the leftmost point.
Okay,
No, parallel to y-axis.
okay,
One parallel to the bottom one, x-axis.
okay, here itself, huh?
No, the bottom.
Okay,
And first I pass one through the no, it is not possible.
But sir, if let's say we don't have to give the slope, then we can choose any of these 2 points and just draw a line which intersects x-axis and y-axis, and that will be a right angle triangle. So how will that work?
sorry, I didn't get it.
In these 2 points left, green points, if we do not have to give slope of the hypotenuse, I don't remember in the question it asked for slope or not, but if we just draw a line, that hypotenuse which passes only 1 point, and slope can be anything, then will it be possible? Anyway, it will create a right angle triangle. But okay, I have to take care of. Yeah, that's not possible. Okay, thank you. I got it.
Yeah. Okay, so any other question?
Sir, can you tell about the what kind of questions we can expect from week 11 and 12? Will there be any numerical kind of questions or just concept-based questions?
Both you can expect.
Okay.
Numerical will be very simple questions that has to do with the randomized response mechanism, right? How does from a data, from a ground truth, how do you go to, you must know how do you go to the randomized response, and that there is a, so from X, how do you go to Y, and then why is Y not enough? Why do you have to do Z? So how do you do Z? How do you compute Z? Z is the final output, right? So you must know these 2 steps thoroughly. How does it happen? And of course, you must know why it is. If you have a small change, if you just change 1 bit, and if you take the probability of the randomized response, then there is some e power epsilon bound, right? So you must know what that bound means. And so data privacy lecture completely, the first lecture thoroughly, if you go through it, that should be enough. Right? Is that fine?
Okay, sir. Yeah.
Sir, also like what kind of topics we need to like revise from week 1 to 6 can be expected in exam?
Week 1 to 6, so kind of need to know. See, the one thing I can tell you is that it won't be too heavy on the memory, right? So you won't have to. The questions you'll be able to solve them without having to recollect some crazy formula that occurs in some corner of the lecture. So it won't require you to remember things like that. It will be more intuitive. So you can expect questions, I'm sorry, from any of the 6 weeks. So it's kind of spread out everywhere. But this point I can tell you, right? So as long as you know the core ideas in those 6 weeks, that'll be enough.
All
Okay.
right.
Yeah. So anything else? Okay. Then I'll share this notebook with you all. Sorry, not notebook. What is this? This notes by tomorrow. I'll just review it one final time, and yeah. So that's all I have. All the best for the exam. This will be the final session, right? So yeah, we'll meet again maybe in some other course.
Yeah, thanks, Karthik. Yeah, Srinivasan here. Yeah, it is definitely a very interesting course, right? And I think we have been warned that it will going to be a tough course, easy course. I mean, not an easy thing, and quite a lot of theory. Very lots of concepts, complex concepts to learn.
Right.
And,
Yeah, that's true.
Sometimes I think it feels that when more I was kind of trying to see why do we need this course. I mean, just as a kind of devil's advocate, right? Asking myself, but if somebody were to question, does AA even work? Does ML even work? Courses like this give us a reasonable amount of points, right? At least to say that
Right.
okay. It's not that this is just built on magic, right? There are mathematical, MLT and those things give the basic foundations, but this give more of the advanced. So that is quite useful.
That is true. Yeah. I also really enjoyed the content.
Yeah.
It's very kind of different. Yeah. Some of them are very hard for this also. So okay. Yeah. SLT. I don't know. Prof. Should ask Professor Arun. He's supposed to do that also. He might do. There is one more course by him. It's like sequential decision making. It's not related to reinforcement learning, but it's a more general for sequence learning problems in general. So that might come. He has already recorded some lectures. He might offer it in January, not next term. January is when it's the earliest we can expect that course. That will be an elective.
Yeah,
So
that's
there
part
is
of the MTech elective. I mean, okay.
Yeah,
It's also
right.
level 6 elective, right? I think, yeah.
Yeah. So there's this whole minor, right? There's a sequential decision. I don't know what it's called. There's some minor which includes RL, this course, ADS, and sequential decision making. So those three form one basket. So he'll surely be offering that, but mostly in Jan. Okay, nice meeting you all.
Yeah,
So
and again,
thanks.
thanks for the first session. And after some time, again, I'm part of the initial thing. Always nice to be I shouldn't say guinea pigs, but yeah, definitely nice to be the first batch.
Yeah, you are right. Yeah.
But kind of came with an open mind. Definitely have a bit more, and I think as somebody asked, right, there is motivation for us also to learn a bit more, right? This gives thing about the theoretical aspects.
Right,
So very
right.
interesting. Yeah, it is a very that way. It is a very I don't know. Maybe Gen A may be similar. But MLOps, for example, was doing it. That is very practical, right? But this one is very theoretical. It gives a good dimension. Thank you, and thanks
Yeah.
for all the help during the.
Sure. Yeah. Okay then. Yeah. Thanks everyone.